Okay, I think we can get started. So welcome everybody. It's great to see that the strike has not completely discouraged people to follow the lectures. And we're glad to have Assa Auerbach for the second lecture of his lecture cycle. So Assa is going to talk today about Higgs mode and other things. Go ahead.
Okay, thank you very much. Thank you for coming. So this is a talk about actually the Higgs amplitude mode in condensed matter, which is kind of an analog of the Higgs particle. It's work actually done by lots of collaborators, and there'll be some experimental, let me see if I can operate this, some experiments I'm going to talk about. And this is one of my collaborators, Dana Rovas, many years ago, wearing a hat that looks like the picture of the Higgs potential. So what I want to emphasize is the appearance of a critical mode, a Higgs mode, which is a critical mode that vanishes at some quantum critical point that could be achieved by changing parameters. This is to distinguish it from other amplitude modes that have been seen in condensed matter and superconductors that are not the critical mode, and I can discuss them later if people want to ask about them. But I'll give a short history. I'll show some examples of amplitude modes, Higgs modes in three-dimensional systems, and then I'll concentrate on two dimensions. Why two dimensions is interesting? Because in two dimensions, there are examples of quantum critical points in experiments. And there's also the interesting question of whether one can see the Higgs mode at all in two dimensions. Two dimensions has a large phase space for phase fluctuations. And since the Higgs mode can decay into phase fluctuations, the question was, for many years, whether or not we could see it. And people assumed we cannot see it because we overdamped into the phase modes. And I'll show that we've actually shown, and now it's quite well understood, that there are ways of seeing it using the correct response functions, called scalar response functions. And another place that the Higgs mode can be seen, which was again a surprise, was in conductivity, in AC conductivity. One usually assumed that in superconductors one cannot see any collective modes through the AC conductivity, and that is now revised, of course, for the suitable models that I'll discuss. And okay, so let me go on. What's the history? I was very pleased to see a picture of Julian Schwinger next to the office that you gave me. So he was the first guy who actually suggested an idea of explaining why gauge fields in particle physics appear to get massive. I mean, why you get a massive, short-range electroweak forces. And that paper preceded the very famous paper of Anderson, which was actually just a demonstration that gauge fields can become massive in metals. Surprisingly, in metals was the first example that you have plasmons instead of, the plasmons actually are representation of a massive longitudinal gauge fluctuation. And plasmons, of course, are known in metals very well. And he gave that as an example of giving mass to gauge fields. But then he, as a bit of an afterthought, in the end of the paper, he said, but if you have broken O2 symmetry, essentially, if you have a superconductor, then not only do you have plasmons, but you also have transverse massive photons. And this is the Meissner effect, where the magnetic field decays exponentially into the sample, because essentially the transverse photons become massive. And he gave that as just an example of how you give mass to gauge fields. Now, he didn't really spend time thinking about what's called the Higgs particle, which is, of course, the things that high-energy physicists thought about, which is actually the representation of the condensate itself. So, in my mind, what is most interesting about the whole Higgs discovery in particle physics is not so much that they found another particle, but the vacuum is not a vacuum anymore. The vacuum is now a superfluid. And that, to me, is amazing. You know, one thinks of the vacuum as being empty, but fact, it's very full of superfluidity. So just to give a short review, which I will not explain, and it's not part of my talk, it's just part of history. In Abers and Lee, there's a nice paper that explains the whole idea of the Higgs mechanism of producing masses to gauge fields. You have a Lagrangian with a gauge field and some kind of a Higgs potential to it, this psi bar psi minus 1 to the second power, and a gauge field. And then there's an assumption that goes in and it's kind of hidden. And when I talk to particle physicists, they all say, oh, yes, you give it a VEV. What do you mean, give it a VEV? You mean that you broke O2 symmetry in some intermediate stage and allow the operator psi, which creates particles, to have a non-zero expectation value in the vacuum, which means that the vacuum is not empty anymore. Anyway, so that's the main assumption that goes in there. Once you expand the order parameter around that one, around that VEV, then of course you get a theory which is massive for the gauge fields, and that's the Higgs mechanism. And on top of that, on top of the massive gauge field, you get a new particle. And the particle is the radial component that oscillates at some high frequency, and that's the Higgs particle. As you can see, this is the Higgs mass. It's just a parameter that depends on the coupling constants, and what was amazing in the particle physics is that they managed to predict it quite well from the different masses and cross-sections of the particles that acquired mass from this mechanism. So that's the high-energy history here. And now I want to go back to condensed matter to see what we really know about this thing. One thing which is kind of amusing is that the actual news that got the high-energy physics extremely excited was this peak that you see there in the particle, in the data. And I see some very good experimentalists in the audience in condensed matter, and I don't think they will go wild if they saw a peak that size in their data. But as you see here, this does have a strong effect on that community. So, which is actually a great discovery, but it's just amusing to see how the data looks like. Once that particle has been discovered, people start thinking about, do we have it in condensed matter? And I started thinking about it by an accidental discovery through calculation. We were interested in understanding hardcore bosons, essentially a picture of bosons which are charged and they're interacting strongly with each other, and the question is what is their conductivity, and we calculated by several different means their AC conductivity. And well, what you expect from bosons at low temperature, this is at 0 temperature, you expect them to be superfluid, and that's the peak that you see at 0 frequency. That's called the superfluid stiffness. This peak here, it's a delta function. It has a weight, which is not the full weight. And the rest of the weight goes into some high energy component, but it looked like a threshold behavior. So this is a calculation based on continued fraction expansion, which I will describe on the technical talk next time. This is exact diagonalization of very small lattice. So, just have a series of delta functions, but there are quite many delta functions here, but that's why it oscillates. And that was something weird, because in theory of superconductivity, BCS theory of superconductivity, I should emphasize, one gets a delta function, but if you have no disorder and if you have no interband transition, there should be no contribution at any finite energy. So what is this peak that you see in hardcore bosons that you don't see in the BCS superconductivity? And an idea came to mind that this might be the Higgs mode, and later I'll show that indeed, when one solves this problem, one does associate this with an amplitude mode, the threshold here, that is the Higgs mass. So that's my own private history on the problem. But I'll just give a short review. Many of you know this stuff pretty well. You have field theories describing Heisenberg antiferromagnets, XY magnets, superconductors. Even solids themselves can be described as a continuum symmetry breaking. And when you write down the field theory, which is essentially a theory that is close to some transition or close to some well-defined phase, then you just expand the potential to quartic order, and you get this Mexican hat. And the Mexican hat will tell you that the ground state will be sitting on the bottom of the Mexican hat. That's the lowest energy, but it'll have some degeneracies. And that's degeneracies will be the manifold of ground states in which the fluctuations are called Goldstone modes. Those are zero energy fluctuations. But there's also a radial mode, which is what we call now the Higgs mode. It's an amplitude mode. And when one writes down a model action, one expects, based on the shape of the potential, just by mean field theory, to have an ordered phase with these two different types of fluctuations, amplitude fluctuations and phase, which is the direction fluctuations. And this holds for this is O2, but it holds also for any ON theory. The number of Goldstone modes is n minus 1. So that's the basic idea. And in experiments, people have seen such modes. When have they seen such modes? They've seen it when they drive the system to quantum criticality. What is quantum criticality? When the barrier in the middle of this Mexican hat goes down and flattens out. When it flattens out, then you can immediately convince yourself that the radial mode becomes soft, right? Because eventually it'll go to 0 at the quantum critical point. And this has been seen in antiferromagnets. It's a beautiful experiment in neutron scattering, where people noticed that they have a longitudinal mode. A longitudinal mode is a mode that fluctuates, that the spins are fluctuating in the direction of the order parameter, not just transverse. And what they saw is when they go through the transition between a Néel-ordered magnet and something which is a quantum paramagnet, or a model where the spins are fluctuating such that there's no moments, there's no long-range order here, this transition as a function of pressure at 0 temperature is associated, as you can see, with vanishing of a longitudinal mode. And that was really a nice demonstration of the amplitude mode in antiferromagnets. There's also modes that can be seen, amplitude modes that can be seen in charge density wave. This is not a quantum critical point, but just seeing a finite oscillation frequency of amplitude mode. How do you excite it? You just shine a pump, you destroy the charge density wave, and then you let the charge density wave recover. And the charge density wave has two modes. One of them is translation, which is the Goldstone mode. That's the soft mode. And one of them is just the oscillation of its amplitude, and that's what's seen in experiments.
So Assa, here we are sitting in the ordered phase. So the
yes.
amplitude mode is gap.
Yes.
And this is why you need to shoot something.
Right, right. Yeah, in order to see the mode at finer frequency, you have to be in the ordered phase. And there's just different nice pictures of these oscillations of the amplitude mode in this system. There's another system a bit less known because it kind of fell off the community interest a long time ago. It's helium-4 solid. Helium-4 solid is a very quantum solid, so it has some differences from a classical solid. A classical solid, as we teach in elementary condensed matter, is built out of essentially particles sitting at a certain position and vibrating, okay? But a quantum solid is those particles are helium-4 atoms, they're very light, and they actually occupy a wave function in this unit cell, okay? They're not really point particles, as the harmonic theory tells you. Now, why does that make a difference? Well, we'll see here a very interesting experiment that's been seen many years ago, but not explained. It's the BCC phase that exists here in a tiny sliver of the phase diagram. And why are we interested in the BCC phase? Because in the BCC phase, we have a Bravais lattice. And in the Bravais lattice, there are only acoustic modes, right? There's no optical modes if you have one atom per unit cell. And as you can see here, both this experiment, they found some mode that as you go to Q equals 0, the mode doesn't go to 0, unlike the acoustic mode, the transverse and longitudinal acoustic modes. This was a mystery. What is this mode that appears here? There was lots of ideas, vacancies and disorder, but these all were not very convincing because it was found in systems that were relatively clean, and also it dispersed. It was kind of like a real mode in the system, not just a bunch of impurities. So we argued that this is essentially another type of Higgs mode. Let me show what kind of a theory he wrote. This is actually a theory done with my student at the time, Snir Gazit, and Eloise Non, who was a French postdoc with us. And we just looked at the Ginzburg-Landau, dynamical Ginzburg-Landau of a quantum solid. And quantum solid is really described by a local quantum variable, which is the density, that can fluctuate. And you parameterize its fluctuation by the Fourier components of the density at reciprocal lattice vectors. And this is a complex number. And this complex number is usually taken to be static. But if it fluctuates, then essentially it describes modes of the system. It could describe both the longitudinal mode, the Goldstone mode, I mean the phonons of the system. But also, what we found is that it can also describe intra-unit cell oscillations when you take G to be non-zero. What does it mean? It means that inside the unit cell, one should think not of a particle, of a helium atom, but of a density that can have an amplitude fluctuation, like a charge density wave. And that is essentially a mode at Q equals 0, because it's the same in every unit cell, and it's massive. It has a finite frequency. So this spurious optical mode was actually a nice amplitude mode of a quantum solid, and that's what we claim. And we did some, Snir Gazit actually did real ab initio with van der Waals interaction simulations of the, with quantum Monte Carlo of the solid. And indeed, okay, sorry, I don't have the, indeed found that one can, okay, with fit with certain parameters, but still the parameters were quite reasonably taken from the known van der Waals interactions, and found that the mode that was actually corresponding to experiment was like a D-wave oscillation inside the unit cell of the helium, the single helium atom wave function. So that's the story there. So these are all three-dimensional systems that have amplitude modes, and as you can see, they're quite diverse. You say, why do we see this mode at low energies, relatively low energies in helium-4? Because helium-4 is very close to other phase, it's close to a superfluid, it's close to other structures, and that's why this mode actually is quite soft. Okay, so now we go to models. The model that is very favorable among cold atoms people which deal with trapped bosons and optical lattices, and also people who do Josephson junction arrays, is a model of lattice bosons. It's a model where you have bosons hopping on a lattice, let's say in 2 dimensions. They have an interaction that wants to prevent them to be on the same lattice side. And they have a phase diagram which is quite well known for many years. It has a continuum superfluid when you look at very weak U. So you can ignore the U, you just have Bose condensation like a BEC. The system will just condense at K equals 0. That's this part of the phase diagram. But as you increase U, you start being sensitive to the chemical potential or to the filling. Because whenever the number of bosons is close to an integer, the system wants to lock into an insulating phase, called Mott insulators of bosons, where you have either one boson per site, 2 boson per site, 3 boson per sites. And these are the Mott phases. And what is nice about this system, it has, first of all, new kind of superfluids that occupy the area between the Mott phases. These are called hardcore bosons, and they are different these superfluids. They have different transport properties, which I'll talk about, but mostly they are highly constrained. They are strongly interacting bosons because they have a constraint that you're not allowed to have, let's say between 1 and 2, you're not allowed to have less than 1 or more than 2 bosons per site on the average, and that's a very strong restriction on its dynamics. But what we want to concentrate here is actually on this point, which is a quantum critical point. It's a point where you go between an ordered superfluid, which is phase ordered, into a charge ordered, or if you want, no phase ordered, phase fluctuation. So it's a very nice example of a critical point of O2 symmetry and described by a field theory, which is a relativistic Gross-Pitevsky, if you want. It has second derivative in time. It has like particle hole symmetry around it. So it has symmetries that you don't have in this limit, which is the Gross-Pitevsky limit, where you have psi star, psi dot, instead of psi dot absolute value squared. So this is the quantum critical point that actually is very much analogous to the high energy theories that people discussed. And the question is, what can we say about the behavior of that system next to that point? The cold atoms people managed to simulate exactly this model. They just put bosons in the lattice, they put a potential, an Egg-Cartan potential. They can make the potential large enough that the number of bosons in some area is locked into an integer. And when they decrease the size of the potential, it becomes a superfluid. The bosons start to hop around and condense. And then in the time of flight experiments, they see very sharp peaks associated with the Bragg peaks of this lattice that show that there is condensation, that there's essentially off-diagonal long-range order, or superfluidity. And the other side, which is actually quite boring in terms of its data, but that's the data of just having a solid where there's no phase coherence between the bosons at different sites. So this transition between high potentials and low potentials really governs this transition of the Bose-Hubbard model. So it's the interplay in the Bose-Hubbard model between U and T. U is the interaction strength. Here it's kept constant. And T is the hopping matrix element, which here is large and here it's small. So that's the description. Another system that can be described by the same model, and lots of experiments are essentially deal with that, are granular superconductors. And here I'm describing actually a Josephson junction array as a model for granular superconductors. I'm not discussing the disorder, but more I'm discussing the fact that the superconductors are confined into boxes that are weakly coupled to each other, and therefore the dynamics become dominated by pair hopping. So what it means is that if you take the energy of essentially breaking a pair to be larger than all the other energy scales of this model, which are the hopping of the bosons and the Coulomb interaction and so on, one can ignore broken pairs and really describe this system as a lattice boson system, again governed by the Bose-Hubbard model. The Josephson junction literature calls this model the ECEJ. This is the capacitance, right? The charge squared of it's essentially a charge square times the inverse capacitance here. This is the superfluid stiffness, or the Josephson junction, the Josephson coupling, sorry, EJ. And this describes essentially trying to form a coherent superconductor across the grains, having to lock the phases. And this wants to fluctuate the density. So, tries not to fluctuate the density, sorry, when this is large. So you have a competition between superconductivity and just insulating behavior where the Cooper pairs are localized and not hopping around anymore. So again, this model is equivalent to the Bose-Hubbard model here. So the U here is equivalent to EC, and the T, the hopping of the bosons, is equivalent to the Josephson coupling. So this model here is what we saw before, has a quantum phase transition when T and U are T over U is of order 1. The density is also important. For this model, it's always picked to be that the density is an integer. So we're sitting at exactly the quantum critical point of this Bose-Hubbard model, the integer density one. But anyway, so that's the correspondence between the Josephson array and the Bose-Hubbard model. So in these systems, one also expects a superconductor to insulator transition, which actually was seen very nice in lots of experiments, but I don't show the references here. Enormous amount of experiments showing very thin film superconductors where you change the film thickness, so you're changing EC over EJ. So as the film thickness goes up, then actually, just a second, as the film thickness goes up, you go down here, you become superconducting because EJ becomes large. And here, EC becomes dominant over EJ, and the system turns into an insulator. And this is a beautiful example of the kind of critical behavior one sees in transport around the quantum critical point. So this was analyzed many years ago, again, in terms of the same field theory that we described before. And this was always called the quantum critical point. However, in order to show that the quantum critical point is bosonic, they had to also do an experiment showing that the gap to break a pair doesn't change between the superconductor and the insulator. Because one of the options of an insulator was an Anderson insulator, where essentially you talk about free electrons in a strong disordered potential and they localize. However, seems to be no free electrons here if the gap doesn't close, because this is also a bosonic insulator, according to this experiment. The experiment shows that the pairing gap, which is an energy scale of forming a Cooper pair on a short scale, is actually unaffected by the transition. And what the physics of the insulator is essentially the physics of a pseudogap. In other words, there is still a gap that prevents the bosons from disintegrating, even though the system is insulating. Okay, that has, I think, implications on other pseudogap systems that I will not describe here. Okay, so the quantum critical modes are these two modes that I discussed before, the phase and the amplitude. And when you go from the ordered phase, actually I should say antiferromagnet, which is more suitable for this model because it's relativistic, and the superfluid model I showed before, relative to a paramagnet or an insulator, this is what changes in the potential, and this is what changes in the mode. So you have here one soft mode and one massive mode. Here you have two massive modes. And this is exactly what is expected. So the amplitude mode is expected to go soft and become a critical mode, and therefore more visible, because the softer the amplitude mode, the less it has room to decay into particle hole or other modes or phonons and so on. So this is how it's supposed to behave close to the critical point. And these are two charge modes. If you ask about the number of modes, they are conserved. You see you have two modes here for the O2 model, and here you have two modes which are actually the two oscillations on this paraboloid. And these are gap charge modes. And the question is, of course, can we see them? Is there a way to actually look at these modes experimentally in the superconducting case? So the visibility was an open question, and I'll explain why, because it's actually an interesting development.
Sorry,
yes, please. Sure.
So what you said is slightly counterintuitive to me in the sense that as we come close to the quantum critical point, the Higgs mode itself is becoming less and less well-defined, right?
Less and less what?
Well-defined.
This is exactly what I'm going to describe.
So, okay, so do you have an experiment showing, let's say, the lifetime or broadening aspects of it, rather than just the...
Experiment? Okay, I'll show the experiment and we can see if that shows, because this has been seen experimentally. But Okay, what you're saying is actually exactly leading me to this question that I want to describe here. So the question is the Higgs mode visible, considering the fact that it can decay? And here I'll show mathematically why it can decay, and why a priori people thought it's not visible, and why we proved it is, okay? And I'll show you that. Okay, so what is the degrees of freedom mathematically? So you expand the order parameter, let's say, around some direction of broken symmetry, and you have the longitudinal direction called sigma and the Goldstone mode called pi, and you expand the action, and the zeroth order harmonic term has a massive longitudinal mode, and it has a massless, right? There's no mass term here. It goes like k squared, longitudinal Goldstone mode. However, there's this term. This term is just continuing to expand the action to third order in pi and sigma, and you find a combination of sigma pi squared. That's dangerous. Why? Because now the longitudinal mode is coupled to two Goldstone modes. And this looks like dangerous, because if it couples to the Goldstone mode, it can decay. The Goldstone modes are lower energy. The other terms are not as dangerous. There's another way of doing it. Actually, the way the field theorists do it. You work in the radial gauge. So in other words, you don't parameterize this as a Cartesian vector. You parameterize as a radial vector and an angular vector. So let's say in 2 dimensions, it's just a radial and a phase, okay? Now you can expand the action, and when you look at the L1 term, interestingly, you don't have a coupling between the longitudinal and the pi squared. You have the radial part, rho, coupled to the gradients of the angle squared. This looks like 2 powers of momentum higher. So the question is, okay, how to do the calculation? So you say this guy has a bit of a less coupling between the radial and the Goldstone mode, or the Higgs and the Goldstone mode, than this guy. But these are just 2 different representations. They should give you the same answer. But let's see what the calculations give. So one can ask, let us calculate sigma sigma. This is the longitudinal response function. It has a Green's function, it has a self-energy, and the self-energy is simply given in terms of this bubble. It has the sigma pi squared I described. If you evaluate this bubble in 2 dimensions, so you have, this is a 2 plus 1 dimension, you evaluate it, it goes like 1 over k, or if you analytically continue, 1 over frequency. So if you look at the spectral function, it diverges at low frequencies. And if you had a Higgs peak somewhere here, because of this m squared, this will completely take over. This goes like 1 over omega. So you won't see it. It'll be like a tiny shoulder. And in fact, what you're asking is exactly right. If I go closer and closer to the quantum critical point, then this becomes more and more hidden, and in the end, you can't see it at all. This was a statement made by several people, Nepomniachtchi, Subir Sachdev, Zwerger, that you cannot see the longitudinal mode, you cannot see the Higgs mode in this way, because of the coupling to the very large phase space of pi. Now, if you do the calculation for a different correlation function, which is a scalar correlation function, you get a very nice peak. Now, the scalar correlation function is using the other approach, which you take rho coupled to gradient of n. So you get 4 powers of k higher between 1 over omega. It will give you omega cube, and it will decay omega cube, and the peak will be visible. So this calculation is done in the perturbative regime of small g. So you're far from the quantum critical point. So the question that you asked is still open. If I come closer to the critical point, would I still have this omega cube, and will I still be able to see this peak of the scalar susceptibility? And I'll soon explain why the scalar susceptibility, which is the response of the radial components to the radial components, is different than the response of the longitudinal components. But this is just showing that it very much depends on which correlation function you use to measure the Higgs. So the simple-minded explanation that I give here is that when you have a fluctuation in the plane like this, and you look at this longitudinal mode, the longitudinal mode is coupled to the pi mode, and there will be like a soft meandering along the rim of the circle, and that will give you, if you want, quite a large fluctuation in sigma, which means the sigma will decay much faster than if I didn't measure sigma, but I measured the radial direction. In other words, if I had a measurement that didn't care about the angle, just cared about the distance of the green line from the center, that distance fluctuates much less than the longitudinal one, because here I essentially contaminated my measurement by essentially a quantity, an observable, that depended on the Goldstone modes. So that's why if one wants to see a sharp mode, it's much better to look at the radial direction. So to give you examples, concrete examples, longitudinal susceptibilities, like in neutron scattering, are like the order parameter correlations. So they will tell you if you broke symmetry in the z direction, what is the fluctuation of SZ as z. Or if you have phase correlations and you broke symmetry and had a well-defined phase, what is the correlation between the order parameter, or essentially the order parameter in the x direction. On the other hand, so these are probes, experimental probes one could use. But scalar susceptibility demand probes that are sensitive only to the magnitude and not to the phase of the order parameter. For instance, if you take the spin squared, that will be a measurement of the radial susceptibility, and it could see the Higgs. So in order to see it, you really have to probe things, especially in 2 dimensions, that depend on the magnitude of that parameter and not on its direction. Also, if you wanted to see it in a superconductor, you should measure the order parameter magnitude squared rather than the order parameter. Why is this Raman scattering? You know, by Loudon-Flory theory, when you have an antiferromagnet and you are sending light, the Raman light will couple to S dot S, like 2 neighboring spins. So in the long wavelength limit, it's like coupling to the magnitude of S squared, assuming that short-range correlations exist. And therefore, Raman scattering doesn't really care about which direction the order parameter is pointing. And it will give you a much sharper peak. Also, I didn't mention here, scalar susceptibilities are the ones you measure with a pulse probe. When you hit the system, so you kill the magnitude of the order parameter at a certain time, and then you watch it recover. So again, you're watching the magnitude or the radial direction, and not the longitudinal direction. So I hope I explained this okay. So that's the why you get this difference. Following our suggestion, Immanuel Bloch actually designed an experiment to measure magnitude of the order parameter in cold atoms by kind of a nifty method. He applied essentially a modulation of the lattice potential. So by that, he essentially modulated the hopping matrix element, which is modulating, again, the order parameter squared at a certain time. This is this modulation. And then he stopped, and then he essentially measured the temperature after a while. In other words, he localized the bosons, and he asked, what is the temperature? So what all this does is measure what is the energy absorption of the system, having been exposed to a modulation at a certain frequency, which is controlled. And what he found is that he gets a peak at a certain frequency, and he can change the depth of the potential through the quantum phase transition we saw before. In this limit, he's in the insulating charge gap. This is the large barrier limit. This is the small barrier limit. And he found actually these 2 critical modes. And you see he comes quite close to the quantum phase transition, and he will still be able to observe this quantum critical mode. So he found this Higgs mode responding to the fact that he's changing the lattice potential and turning in the system from this is the superfluid phase, this is the insulator phase, right? And the nice thing that made us happy is he also measured the frequency dependence response function, and it did go like omega cube as the simple calculation gave. Okay, so it really showed that this was at some distance from the quantum critical point. There still was the question of what happens exactly at criticality. Do you still have the peak and the omega cube term? That was like an academic question, but since we could do, well, Snir-Gazit could do Monte Carlo at very high accuracy, large systems, he was able to also get some results, I saw it later, for close to the quantum critical point. So now I'm coming to theory of superconductivity everybody knows and loves, BCS theory, and asking what is the AC conductivity of BCS theory? So I'm sure that anybody in the field knows these answers, but they're still quite interesting to discuss. So the BCS superconductor with one band, no disorder, has a very simple response. It has a delta function at 0 and nothing else. Why? Because the BCS Hamiltonian in the mean field limit, okay, when you write the BCS Hamiltonian as kinetic energy plus C dagger times delta plus delta star CC, if you write that BCS Hamiltonian commuted with the current, turns out it commutes. And if it commutes, there will be no AC conductivity. If you don't want it to commute, you have to add more bands, and then you have interband transition, and you'll get essentially something appearing above a certain interband energy. And if you put disorder, you would actually get the Matisse-Bardeen behavior, which is the one you mostly see in systems because of, most systems are slightly disordered. And the Matisse-Bardeen actually starts at 2 delta. And it's dominated essentially by particles excited above the gap. There's no momentum conservation, so that allows you to see this contribution in the AC conductivity. And that's what people always analyzed superconductors with. However, it's not an exact theory, even the BCS model is not exact, but the BCS mean field theory essentially is not exact. If you take the interacting electrons theory with a 4 fermion interaction, you do get a contribution of non-commuting current and Hamiltonian that will give you a contribution. If you want to see the Higgs, you really need very complicated diagrams that nobody ever wrote down, because essentially what I'm saying is that it will come from the 4 boson interaction. These are the 4 Cooper pair interaction you have in the O2 field theory that drives the quantum critical point, that drives the quantum phase transition, but is lacking completely in the BCS mean field theory. So it's very difficult to see this Higgs mode within this theory. However, one didn't expect to see the Higgs mode in a general superconductor, because if you calculate what is the distance from a quantum critical point, which is quite large in general, that mode should be much higher than 2 delta, because 2 delta is a tiny number in ordinary superconductors. 2 delta is exponentially smaller than the Fermi energy, and the Higgs could be much larger, and then it would decay into particle Hall excitation, and you won't be able to see anything special. In general, people didn't worry about this Higgs particle in superconductors because of that. But if you look at the O2 model, this model it's a bosonic model that has a quantum critical point, and you calculate the current-current correlation function, then the current is given in terms of this product of the radial and the transverse, or the longitudinal and the Goldstone modes. There's this kind of a combination that defines the current. So when you calculate the response function, finite frequency, you have these bubbles where this is massless and this is massive. So when you calculate the response of this function, you get a threshold where you'll start getting dissipation once the frequency becomes larger than the Higgs mass. And then there is corrections of higher order in the coupling constant. So this is how it looks like. So in 2 dimensions and 3 dimensions, you get a threshold. The threshold is exactly the Higgs mass. The prefactor depends on dimensionality. It will tell you essentially the phase space of the Goldstone modes in these dimensions. And that is a signature that is expected if the Higgs mode is low enough in a superconductor relative to all the other energy scales that come in also. So this calculation was done perturbatively, also with a large N expansion, and gave us essentially the functional form that essentially explained those things we saw in the hardcore boson simulations I showed you in the beginning. The other terms here of higher order in the coupling constant will give you a subgap tail, like we have for the scalar susceptibility. It goes in 2 dimensions, it goes like omega to the 5th. So it's very small tail, but overall it won't change the fact that you see a nice threshold. Okay, and this was actually checked numerically very close to criticality, just to make sure that all these features we're talking about survive when you come close to the critical point. The first calculation is actually by Damle and Sachdev many years ago. It was confirmed numerically by Monte Carlo and by analytic continuation. The analytic continuation is the reason for all these oscillations. So what is most important to look at is there is a threshold appearing in the analytically continued Monte Carlo data, which shows a charge gap in the MOT phase, in the insulator. But that's not surprising. We expect a charge gap in the insulator, and that charge gap it's an insulator, right? Should give you no conductivity. But in the superfluid, this analytic behavior I showed you before was nicely confirmed with Monte Carlo to scale with the size of the Higgs. Okay, so there's a delta here, and there's a Higgs mass, and they scale nicely together. In other words, if I take the mass to 0 and delta to 0, I'll keep this shape. So the threshold doesn't go away, it just goes down. So it is possible to observe in the conductivity and in the scalar susceptibility these features all the way to the critical point. And we also get some high frequency conductivity. Let me go further. And these are experiments. So the experiments here were done on disordered granular superconductors. And what they showed is that there's a gap that survives both in the ordered and disordered phase. And they started changing the density or changing the thickness, and they plot the optical conductivity, and they also plot what would be expected from Bardeen-Stevens theory, they call it BCS, with the same delta they measured in tunneling. And you see there's a marked difference. In other words, the threshold of conductivity becomes lower than the gap measured in tunneling. And the argument was they're seeing essentially indication of the amplitude mode becoming soft and dominating the optical conductivity. And this work, this was actually plotted a bit more systematically by looking at the film thickness changing here towards the quantum critical point. This is the insulator on this side, and the Higgs mass falling down. This is the threshold of the conductivity, and the tunneling gap not falling down as much. This is a log plot, okay? So this work actually, I think, was nice in the sense that it was the first time the superconductor-insulator transition was actually related to a quantum critical point in the true sense of the word. Not just seeing diverging resistivities, but finding the object that becomes critical, or the correlation length. This is a time correlation length, right? The mass is the time correlation length diverging at that point. Without those diverging correlations, it's difficult to prove that you have a critical point. So that, I think, is the important part. However, that said, this paper received a lot of criticism for over-interpreting the data because disorder is part of the system. So it's not a regular Josephson array. It's not ordered in the sense of having translation invariant on the lattice of Josephson array. It's a random Josephson array, actually. And the question is, how different, or what is the effect of disorder? It smears the transition. It does a lot of, it messes up the definition of the excitations and so on, and the the fact that you have a well-defined wave vector. But I don't think that this result is going to change much, but I hope somebody will really do it on an ordered quantum Josephson array. The problem with the quantum Josephson array is you have to make the junctions very, very small to have a high energy of interaction, or in other words, a small capacitance to get to the quantum limit. Anyway, so that's the situation in the Josephson array. This was numerical work, which was done. It's essentially taking all the numerical work I was discussing before by Snir Gazit and showing that the superfluid stiffness, which is measured numerically, vanishes with an exponent 0.677, which is the three-dimensional XY exponent, best known number. The Higgs mass falls down with the same exponent. So the Higgs mass is related to the superfluid stiffness locally and is critical with the same correlation length. And the charge gap, again, vanishes with the same correlation length, but on the other side. And there is also a new object that could be measured. The theory of, actually, this was a theory by Matthew Fisher and Dang-Hai Lee that said that this quantum phase transition is interesting because it has duality between the charges on one side, on the superfluid side, and the vortices on the other side. So in other words, here you have like a condensate of vortices, here you have a condensate of charge. And if you have a condensate of vortices, the question is immediately, what is their stiffness? So the stiffness is really the capacitance of the system here. And that capacitance could be measured. It's the inverse of the imaginary susceptibility, and it also is critical. And we could also get the relation of amplitudes. What we see here is that the duality is not exact because the coefficients of these scaling behaviors, these functions, are not the same on both sides. But one does not expect charge-vortex duality to be exact because charges interact locally with short-range interactions and vortices interact with long-range logarithmic interactions. Okay, one last example of quantum criticality measured by a bystander, which are the d-paired fermions, was done actually in collaboration with the Bar-Ilan group and the Grenoble group, especially Olivier Bourgeois, who did very sensitive heat capacity measurements on disordered films close to the quantum critical point. And of course, Nicolas Dupuy. And all this experiment really shows is that when one looks at the heat capacity measured close to the metal insulator or superconductor insulator transition, it exhibits the gamma term in this heat capacity, which is C over T. It exhibits a huge enhancement towards the insulator. That's strange because naively speaking, people say in insulator you have no density of states for fermions and one should get a reduced heat capacity. But here you get an enhanced heat capacity, and we say that this capacity is enhanced because of really the underlying order parameter that is becoming critical. And that's the softening of the Higgs mass that will give you a large contribution to the heat capacity. So this was a scaling analysis. You take this gamma term, and it turns out that this gamma term does follow a power law minus alpha of Tc over T. This behavior for fermions that are interacting with an order parameter that goes critical is actually very well known in the field of quantum criticality in metals. And this is a review article showing, how you get these power laws in fermionic behaviors next to quantum critical point in different types of quantum critical point with different factors. We're not relating our theory exactly to this is a phenomenological review, but we're not relating our theory to any particular system here, but it just shows that the measurement of specific heat of fermions can actually tell us what they're coupling to, and if they're coupling to something critical, you'd see anomalies there too. So that's the stuff on the quantum criticality. How much time do you have now still? 5 minutes. Oh, okay, great. I just want to summarize not summarize, arrive at a subject that's close to my heart. It's superconductors at strong coupling. Superconductors whose interaction, the pairing interaction, is quite strong. So the Josephson array is exactly that limit, because you're taking the pairing interaction to be stronger than the superfluid density, than the mobility of the holes, of the pairs. But even without that, if just one looks at the coherence length of superconductors as measured by HC2 and by this very nice old paper by Guy Deutscher, and you see the coherence length in superconductors is in the micrometer scale, but when you go to these lower states of matter, which are cuprates and fullerenes and pnictides and so on, you get out of the BCS regime, which is kf psi much larger than 1. If kx psi becomes of order 1, you can think of it as tightly bound pairs, because that's the distance essentially between pairs becomes shorter than the distance between electrons. Now, all this is just statements, right? It's not any particular useful in terms of calculations, but one says that in this regime, one could think that the system would behave like hardcore bosons in its transport and also perhaps in its Higgs modes. So why do I mention the Higgs modes? Because there's a very old problem. One of the first problems I heard in the high TC when it just came out. The optical data was strange. At low temperatures, it showed this shoulder at 500 centimeters minus 1. Now, why was it strange? People knew that it's a D-wave superconductor, and the Bardeen-Steven theory didn't seem to agree. The Bardeen-Steven theory, Mattis-Bardeen theory did not agree because it depended on disorder, it depended on the nature of the wave function of the order parameter, symmetry, and so on. And there were huge arguments. Where is it from? Why is there a threshold like that in the it was called the mid-infrared peak at 500 centimeters minus 1. And very recently, I saw some papers coming out doing Raman and both predicting and also observing a peak at 500 minus 1. And Raman, as I said, is a scalar susceptibility that's actually useful for measuring amplitude modes. So without sticking my neck out too far, I think these guys could be right. They are actually associating this with fluctuations of the order parameters magnitude. And anyway, so I don't think it's a coincidence that they get essentially the same frequency as the threshold seen in the optical IR. Okay, so I can summarize. What did I talk about? I talked about the ON model and about its quantum phase transition. I talked about the representation of the fluctuations in terms of Cartesian and polar, and the fact that the Higgs mode can decay, and therefore one should look in 2 dimensions especially for radial responses or scalar responses relative to order parameter responses. And one could also see the behavior or the Higgs mass in terms of threshold in the conductivity. And there are lots of beautiful experiments that show different aspects of the Higgs mode that I discussed. And this is stolen from my friend Dan Arovas, who shows this at the end of his talk. And then he says, well, they were searching for the Higgs mode for a long time, and then discovered Phil Anderson. Okay, thank you.